So hi students, we're going to have the last week of our class, and actually our class, officially our class finishes on July 9th, which is the Thursday, okay? So July 9th, Thursday, okay? So officially you need to finish all of your homeworks on this date, so that I can have enough time to do the grading. But what I do is that I'll give you one more day, okay, until July 10th. So you have the opportunity to submit all your exercises on my programming lab, and I'm going to do the grading right on the Saturday after that. So no more extension can be given, okay? So and also previously I received a couple of emails saying that, okay, suppose I try a lot of times on the same exercise, on the same question, and so that's finally I got it correct. Am I going to receive the full credit? The answer is yes. No matter how many times you try, as long as you got it correct, you will be able to get the full credit. Okay, so so take your time, and if you haven't finished most of your assignments, it's time to do so. Okay, remember, most actually not most, all of your grades are just depend on the exercises on my programming lab. So take it seriously, okay? And today we're going to discuss the last topic named say recursion. So recursion is programming logic, and it is not widely used, but it's good to know this logic. So so here we only need to focus on the first 4 sub-chapters, and in my opinion the most important part is the recursive thinking. So recursive is another way, or it's kind of like it's just a different way to solve an iterative problem. So let's look at what it does. So first, a recursive definition is one in which one which uses the word or concept being defined in the definition itself. It's like the definition of something depends on the definition of yourself. So this is quite abstract, right? So let's look at an example. So suppose here we're considering a list. A list can be a combination of numbers and comma, a list of numbers that are separated by comma. Okay, so this is our definition of list. But how do we define them mathematically? So we can define them in this way. Okay, a list is either a single number, or it can be a number plus a comma, and plus another list. So the first one we call it base case, because it's the most simple case. So in this case, our list only includes a single number. So for example, if we consider a list, it can be like just this one, 24. So this way, the second definition is a more complicated one. So for example, if we just look at a list with these values like 24, comma, and 88, so it definitely goes to this way. Okay, so we have a number which is 24, a comma, 88, and another list, which is in this list it only includes one single number, which is 88. And also, so here we can, if we have a more complicated case, so we have this one. So here it also falls into the definition of the second one. So here we have a single number, over here we have a comma over here, and this whole part belongs, this whole part is just another list. So this kind of definition, is very easy for us, for human beings, to derive, and so if you look at it, okay, the definition of list depends on the definition of itself. So list appears, so here we have an equation, and in this equation the list appears on both the left and the right hand side. So this is called a recursive definition. And so in programming we have a way to recursively solve problem in a pretty much similar way like this one. Okay, so here people just show an example of, in the programming language of list. List is a functional programming language, and you are not going to learn at Montclair, and in most cases nobody uses this language nowadays, because it's just too theoretical and it's too hard to learn. But in this language, in any say functional programming language, recursive or recursion is widely used, especially recursive definition. But luckily, most of us never touch them. So here we have an infinite recursion, so you don't need to pay much attention to it. So let's look at another definition of recursion. So for example, here we are considering factorial numbers. So the factorial of say 3, we use this symbol to denote. Okay, so this is the factorial over 3. So it's basically 3 times 2 times 1, and the factorial of 4 is basically 4 times 3 times 2 times 1. So here you can say that the factorial of whatever is so the factorial of n is basically n times the factorial of n minus 1. And in the base case, we have one that we have the factorial of 1 equal to 1. This is the most simple case. There is no 0, the factorial of 0. Okay, so if we look by following this example, we can define the factorial operations or factorial numbers in a mathematical way, which is here. The factorial of n is 1 if n equal to 1. Otherwise, it is basically n times the factorial of n minus 1. Otherwise, okay. So here n has to be a natural integer number. So this is the definition of factorial, and here we can see that the definition of factorial depends on itself, because on the left hand side we have the factorial operation, on the right hand side we also have the factorial operation, right? So this is the factorial say definition, and here following this one, following the factorial following the recursive definition, we can come up with a recursive way to calculate the value. Okay, so here say we can just create a function called public integer factorial, and here we take an input, an integer n as the input. So in this function, we basically want to calculate the factorial over n and return it. So how do we calculate? So first, if n, we just follow we go back to the definition. First, we handle the base case. If n equal to 1, we just return 1, right? Because the factorial of 1 is just 1. So else we return n times the factorial of n minus 1. Exactly the same as the second case over here, the more complicated case, n times the factorial of n minus 1. So here we call in the definition of the function of factorial, we call the function again, but we just use another input parameter, which is n-1, and this is called a recursive function. A recursive function is a function in which we call the function itself. So this is pretty much the whole concept of recursive definition and recursive function, in my opinion. So when you handle your problems, better start from the recursive definition. First, write down the formula, the mathematical formula, by using a recursive way, and then so you come up, you just translate this recursive formula, mathematical formula, into your program, and this step is very easy. So this is extremely easy. Once you have the recursive definitions, it's very easy. But from your detailed problem, it's hard to abstract into the mathematical equation. So this is pretty much the recursive factorial example. So let's look at recursive programming. So recursive programming is, as what I said, is basically a function in which it calls itself. Okay. And one thing that we need to know is that, okay, so in most of the cases, so a recursive function can be replaced by a recursive function can be replaced by an iterative function. So you can, for the same function, it's like to accomplish the same object, we have different ways. So on the left hand side we have the recursive way. On the right hand side we have the iterative way. So the pro or the advantage of the recursive way is that, so it's easy for you to derive the it's easy for you to understand the problem and reach. It's easy for us to understand, basically. Like over here, once we get this formula, sorry, once we get this formula, it's not too hard for us to reach the recursive program. But the cons is that, okay, the pro is over here, but the cons is here. Okay, it's slow. When you execute the program, it takes longer time. Okay, so in the industry, people try to avoid recursive, but advocate iterative functions. Okay, so this is something that I need to let you know. So for example, here we want to calculate the sum from 1 to n. So let's say we want to calculate the sum from 1 to n. If we got the recursive definition, so if n equal to 1, if n is 1, then we basically wanted to return 1. Otherwise, we just wanted to return n plus the sum of n minus 1, right? So this is the else way. Okay, so here we can come up with, let's focus on the recursive function, which is right over here. Okay, this is the recursive function. If the number is 1, it just returns 1. Otherwise, it returns the number plus the sum of n minus 1. So here, I believe that this one is a typo. It should be number minus 1, and then return the result. Okay, so this is again this is a recursive function, a recursive version of the sum function. And then so if it's good for, so if you are trying to solve the problem, it's good enough for you to reach here. Okay, because you got the solution, you got the function which can help us to calculate the sum from 1 to n. But actually, if you are in the software engineering industry, it's better for you to translate this function to an iterative function. Let's define the function, come up with the function so with the same purpose, but it's just an iterative function. We want to avoid the recursion. Okay, so let's say what this does. So we basically want to calculate the result from 1 to we basically want to do the sum from 1 to number. So so here we just create an integer. Let's call it result. And then we create a for loop for starting from 1 is less than or equal to number I++ result add plus this I. So here with this for loop, we're basically going to add every number from 1 to number to result, and then we return result. Okay, so on the right hand side we have the iterative version of this function, and so yes, they basically do the same thing, but if you run them, especially if you use a large number, say 10,000 or 1 million, you will be able to notice that the iterative function is significantly more efficient than the recursive one. Okay, so yes, if it's possible, you should definitely go for the iterative version of the function. And then so this is what I just said. It doesn't mean that we should use recursion. Okay, and then let's look at two examples. The first one is called traversing a maze. So a maze is something like this. So it's a matrix. It's a matrix with ones and zeros. Ones means that you can go from so there is a way for you to go over here. So if it's a 0, it means that it's blocked. You can't go. So in this problem, we want to find out all possible ways that can help you to go from the top left over here until the bottom right. Okay, so this is the setup of the problem, and here we want to output all the possible paths from the beginning to the end. So here you can see that 777 means that there is a way to go to. So you can go. It means that you can go. Okay, so here 777 means that there is a path. Go over here, and so let me just explain one path. So from the top left, we can follow the 7s to go in this way, and then in this way. So you'll be able to reach over here. Okay, the 3 means that you have tried this place, but so this place won't give you a path. So for example, if you go from top to this place, so basically you have no way to go, no other way to go, because you are only facing zeros. Zeros meaning the road has been blocked. Okay, so this is the problem. And how do we handle the problem? So here we want to mark the places that we have tried but not successful with 3, and we also want to place 7 at those places that can give us a path. And this is our input. Okay, so this is our input. We have a grid, a 2-dimensional array. So this is the traverse function. So basically here what we want to do is that. Okay, so suppose that, okay, we want to do the traverse. We want to define the traverse function. and we're at a position with index I and j, meaning that at the ith row and jth column. So for example, we're at right over here. Okay, so here we need to handle the following cases. If I and j are at the end of this grid, okay, so if we are at this place, if we are not at this place, if we are at this place, it means I equal to the, let's say this grid size is let's say that means x times y, so meaning that we have x rows and y columns. If x equal to x minus y, meaning that we're at the last row, and if j equal to y minus 1, meaning that we're at the last column. So meaning that we are already at the destination, the place that we want to go. So we will return true, meaning that we find a path. Okay, we successfully reach the path. Otherwise, meaning that we are not at the place yet. We are not at our destination yet. We need to try to go either go up or go left or go right or go down. So here we basically want to go traverse I plus 1j, traverse ij plus 1, and traverse I minus 1j, and traverse ij minus 1. So with I plus 1j, meaning that you are going one row below, okay, and with I minus 1j, meaning that you want to go above, you want to try the row above. As long as any of them can give us a path, we are going to return true. Otherwise, we just return false. So this is the logic of this program. And here you can see that we basically define the solution in a recursive way, because on the left hand side we have traverse, on the right hand side we also have the traverse. So this is the solution following the recursive definition that we just provided. So here the traverse function takes two input parameters, row and column. So initially we set a boolean, we set down as false, down meaning that if we reach the destination or not. So if valid row column valid basically checks if this place is a 1. So if we have a 1 marked at this place, if this place is valid, then we are going to say mark this place with tried. And then this is the first case as what we discussed. So if it already reaches we are already at the destination, we will set down to be true, and then just return it and mark the corresponding place with 7, with path 7. So otherwise we're just going to try to go down or go right or go left and go up, as long as one of them returns as true, meaning that so we successfully find a path, then we also mark it with path, and finally we just return the value down. So this is what we got. And so if you type in the program, you should be able to get the result over here. Okay, and then let's look at another problem. This problem is called the Towers of Hanoi, and this problem is really sophisticated. So let's so here we have the problem set up. Suppose we have three vertical packs and several disks from small to large, and initially we have three disks piling up at the first pack, and so from small to large. So you will need to move all of them to the last pack, and so you can only move one at a time. And also another restriction is that a larger disk cannot be put on top of a smaller one. So the solution to move all of them to the last pack is here. So first, you move this one you move the smallest one to the last pack, and then you move the middle one to the middle pack, and a medium-sized one to the middle pack, and then you move the small one back to the middle one, and then you move the largest disk from the first pack to the last pack, and then you move the smallest one to the first pack, and then you move the medium-sized one to the last pack, and then finally you move the last one the smallest one to the last pack. So this is the procedure. Okay, so how do we solve the problem? If you look at the solution, you'll be shocked by how easy it is. So the solution is right over here, and it takes 4 parameters: number of disks, start, end, and temp. So start it tells you, okay, at which position. So are these disks at which pack? Okay, and meaning that you want to move all the disks to which pack. And temp means, okay, we can use which one as the temporal or the transition point. So if the number of disks equal to 1, it means that, okay, you only need to move one disk from the start to the end, and it's quite easy. You just move it, you just carry it over, and this is the function. So we say we just move one disk from start to the end. So otherwise, look at here. Okay, so you will need to move all the all the disks except for the last one from the start to the temp. Okay, here it's to the temp. So and then suppose over here the problem is that, okay, in the beginning we need to move 3 packs from the first one to the last one, and this is temp. So to solve the problem, you will need to move the first 2 to the temporal one, and then you move the last one. The largest one to your destination to the end pack, and then you move this number of disks from the temp to the end. So just 3 steps, right? So, and this is what the program tells us. So we just move all the disks except for the last one from the start to the temp, and then we move the last one from the start to our end. Then we move all the other disks from the temporal one to the end. Then we just solve the problem. So this is so if we look in the details, okay, this function is calling to self. So this is a recursive function. Okay, and with the recursive function, it's kind of like easy for us to figure out the logic. Yes, it's beautiful, but if you run, it's not going to be very efficient. Okay, so this is the end of the lecture, and so please do your homeworks on Mac Programming Lab, and also enjoy the rest of your summer. Thank you.